view of what is given. We have a combined transmission. On the upper side, we have the hydrostatic variable transmission. This question is given that V1 is half of V2, so I take it as V and 2V. These are the displacements. And some further conditions are given that here we are using a differential gearbox to combine the RPMs, because the differential gearbox has this equation R omega R plus R omega S equals 2R omega C. It's like a planetary gearbox. But that combination has already been done for us, and we know that the output RPM, what we are getting here, is Nm plus N2. N0 is Nm plus N2, and output torque has been given to us as 200 Newton meters. On top of that, we also know that the torque in the mechanical transmission, the mechanical part, is 200. And we know the torque that is coming out of the hydrostatic drive is 200 Newton meters.
We can use the hydromechanical.
What we don't know is the T1, and the input torque is basically T1 plus Tm. But let's first start with the volumetric flow to get the output RPM, the RPM of this shaft. It's going to be nearly half because the displacements are half, but we have in between the volumetric efficiency.
In this part, is it going to be 2V1 is equal to V2?
Yes. 2V1 equals V2. Right. So let's look at the Q effective. I'm taking the displacement as some V. Q effective out of the pump is N is 1479 times V, which is just a variable that I am setting, and this is going to be in, let's say, liters per minute. Doesn't matter because the V unit is going to get cancelled in the end. It's not just 1479 times V. I have to multiply the volumetric efficiency on top of that, because it doesn't give the full one. The volumetric efficiency 0.9 is multiplied. Now on the drive side, the Q effective I divide with the displacement, which is 2V. So that is 1479 times V times 0.9 divided by 2V. But that's not all. I also need to consider the efficiency because it uses more fluid than it's supposed to. So I have to multiply the volumetric efficiency again. So the VV get cancelled and the N output RPM here, it is N2. N2 comes out, what's the value? 1479 times 0.9. Multiply 0.9.
598.99.
Okay, so basically 599 RPM.
Just a minute. So you took Q effective of the pump.
I will explain again.
Basically, volumetric efficiency is basically a Q effective over Q theoretical, right?
So what I am doing is basically the conservation of mass or conservation of flow. Whatever Q is coming out here is getting used here. But the drive is not fully efficient. It doesn't use the Q perfectly to give me the RPM. So if it uses the Q perfectly, there will be no N volume term. I just divide the Q by 2V, and this is the displacement to get the RPM. But because it's not perfect, I have to multiply the volumetric efficiency on top of that to get the RPM.
One thing, we calculate Q theoretical through the formula, right?
Not Q theoretical, I'm getting Q actual,
Because we are multiplying it by the
volumetric efficiency.
volumetric efficiency.
Correct. So if we just had the RPM and the displacement, I get Q theoretical. I multiply volumetric efficiency to get Q effective, Q actual, and I use this Q. This Q actual is the Q actual of the pump itself, and that becomes the Q theoretical for the drive. But that's not perfect. Basically, it's like, let's say the drive is supposed to use 100 liters per minute to make 1000 RPM. But now when I actually give 100 liters per minute, it makes 900 RPM because its volumetric efficiency is 0.9. It gives lesser RPM than it's supposed to for the volume I give. That's a more logical way of thinking. That's why I have another 0.9 here. And that gives me 599. And then I can get the answer Nm plus N2. Nm is known to me because these two have a reduction ratio of 1, so 1479. So output N0 is 1479 plus 599 1 by minute. Right, that's for the RPM. Now we need to look at the torque calculation. Torque, like I said before, T in equals Tm plus T1. My challenge here, the problem here is to find T1 from T2. Here I have to use the hydromechanical efficiencies in reverse because I am getting the input from the output. So one correction with what I did. So to calculate the torque T2, we should be not only considering the hydromechanical efficiency but also the ratios of the displacement, because otherwise the law of conservation of energy is not met. Again, I am taking the ideal case where all the efficiencies are 1. So whatever RPM 1000 I give becomes 500 because of the displacement ratio. This is very clear. So if I have 100 liter per minute, and the displacement, let us say, is 1 liter per rotation, then I will get 100 rotations per minute. So just consider that the flow rate is 100 liter per minute. The displacement here, V is 1 liter per rotation. That means I get 100 rotations per minute. And this displacement is half. So this is 0.5 liter per rotation. So this is the ideal case where all the efficiencies are 1, which means it should have rotated 200 times in a minute. To get 100 liters per minute. 200 times 0.5 is 100. Now let us say I am getting some output torque T here. What should be the input torque? So since all the efficiencies are 1, power is conserved, so let us say this is T1. T1 times 200 has to be equal to T times 100. So T1 has to be T by 2. So basically the input torque is output torque by 2. So T1 by T2 equals V1 by V2, the ratio of the displacements. And now on top of that, we will apply the hydromechanical efficiency. So T1 by T2 equals V1 by V2. Let me turn that upside down. T2 becomes T1 V2 by V1, and that is without considering the efficiencies. Once you consider the efficiencies, you have to multiply that. So eta Hm square. Now I want T1 from this. So T1 equals T2 times V1 by V2, and the denominator is also eta hydromechanical. What is T2? Is 200. 200 divided by 0.5. 200 divided by 2. Sorry. 200 divided by 2 because V2 is 2V and V1 is V. 200 divided by 2, and then eta hydromechanical is 0.92 square. How much does that give us? It's probably half of this, which is 1 118 Newton meters. That gives me 318 Newton meters. This is correct. And now we want to find the efficiency. Efficiency is very simple because we have the input torque, which is 380 Newton meter. We have the input rotational speed. We have the output torque. We have the output rotational speed. We found that here. From that we can get efficiency. What's the value of this? Plus 600 is 2078. Now to get the efficiency, eta equals P out over P in, which would be P2 times N0 multiplied by 2 pi by 60 divided by T in times N in into 2 pi by 60. The 2 pi by 60 terms cancel out, giving us T2 is 200 Newton meter. What is NO is 2078, 2078 1 by minute.
N in is 1479, right?
N in is 1479, right? No, it's 1470. Oh, okay, I was taking 79. What is the adjusted value? 1470.
595. Now you are getting the exact answer. 2065. 2065.
2065. Okay. And that is the output RPM. Input torque is not changing because of all this. It's still the same 318 Newton meters. 318 Newton meter multiplied by input RPM is 1470.
So efficiency is coming at 0.88.
This is 0.88.
Is it overall?
Yeah, it's overall because input RPM, output RPM. It's the overall efficiency. 0.8835. You might think, why can't I just directly use the volumetric efficiencies and the hydromechanical efficiencies, multiply all that to get overall efficiency, like we do in a hydrostatic drive. You can't do that because we have in between a mechanical drive which has 100% efficiency. So then to do that, you have to calculate how much power is going through here, how much through there, and then you have to find a weighted average. Instead of that, the direct method of output power and input power is better.